Welcome guys to episode 7 of our ReliaCast series. Each episode we cover reliability engineering topics, and if you haven't seen them yet, please check them out on LinkedIn and YouTube. We have now 6 episodes prior to this, hence episode 7. We're bringing things together. I've got with me today Sam Eisenberg. Welcome, Sam.
Hey Chris, glad to be
Welcome
here.
back.
Thank you.
Yes,
looking forward to
welcome
talking
back.
about this.
Yeah. So yeah, so you joined us in the previous videos early on, and we've had some a little bit of a journey in the lifecycle engineering discussions, and we're on now for today's topic, which, as we promised in the last video, that we talk more about it, is RAMS analysis. So that's reliability, availability, maintainability, with respect for the safety. So there's the analysis leading into the safety, and that analysis feeding one of the tools that's used, fault tree analysis. So myself and Sam, we're going to be talking about that topic for today. The prior videos that we've been through, just as a recap, for some of the topics, we've discussed life data analysis, we've discussed feeding into failure modes and effects analysis, and from that failure modes and effects analysis we can include failure modes and reliability analysis, and then finally the RCM, so reliability centered maintenance. So from those we can generate reliability, availability from the RCM tools, and also the understanding and analysis of the maintainability. So bringing those together, Sam, would you like to summarize
Sure.
how these things come together and how these become a useful concept?
Yeah, so I mean, really, there's two subjects here, because there's sort of a differentiation between RAM, meaning reliability, availability, and maintainability, and then RAMs, where we introduce safety. And typically, there's actually a bit of a split out between the two. And so I'm sure we'll get to that in probably 5 or 10 minutes. But just sort of a preview of, generally speaking, we're talking about two teams here.
Yeah.
So when we're talking about bringing everything together from just the RAM perspective, before we start bringing in the S at the end of that, we're starting to look at how we are incorporating all of the reliability evaluation we've done so far. So, I mean, with the FMEA, we're not fully into the reliability world in terms of the numerics and statistics. We're more looking at the pre-reliability things, the things that are going to factor into our reliability of our design or of our process. But as soon as we start transitioning into any of the post-FMEA activities, we start talking about the actual reliability and whether or not that's the real or the predicted reliability. Real usually comes from previous versions of the same system. Predicted usually means we've got some sort of standards-based prediction to make some educated guesses with. But we're starting to talk about the sort of concert of all of our activities coming together, and then trying to get an idea of how reliable that system is going to be. And so that's where RCM, or in the case of some of these things, a couple of topics I'm sure we're about to discuss, are going to be fault tree diagrams, or even their slightly more complex brother, reliability block diagrams. But those all start to come together to deal with the reliability of a system, as opposed to the piece part reliability of all the constituent pieces of your system and its system of systems of systems. So there's a lot of this that sort of feeds up as we go, so that we can get the overall reliability or the overall maintainability / availability of a system. There's one other topic that I don't know that we're going to go into depth with today, But there's the notion of, if we're talking about availability and we're talking about maintainability specifically, then we are no longer talking about instantaneous reliability as a point in time. We're talking about continuous reliability functions, where we're tracking how the reliability of a system is, not just at 100 hours, but what the integrations of all those reliabilities are over time, so that we can get an idea.
It will be useful, yes, to go down that path, because I say in previous videos we've covered FMRA, which is the point reliability analysis. So taking that FMRA, and we'll take that on a journey into the simulation aspects of it. We've mentioned BlockSim a few times in previous videos, and with that BlockSim tool, yes, bringing in the FMRA data, as we discussed in the previous videos, and getting that FMRA data together, we can then start to do that analysis. So yeah, please carry on, Sam. We're definitely going down that route.
Appreciate it. The biggest thing is, so what we're really talking about is how to bring all of those things together. And so, this means, is our system being actively maintained, or is it being passively maintained? Do we have conditional based maintenance policies? Do we have responsive or reactive based maintenance policies? Do we have run to failure maintenance policies? How are we choosing to manage that? And then bringing all of those things together and using the other tools in the tool set, like you just mentioned. We're talking about the RCM pluses and the BlockSims of the world, where we're looking at getting through the Monte Carlo simulations of all of those reliability factors and those maintenance tasks. We get our anticipated availability pieces by factoring in our maintenance policies. And that's where we get the basic RAM portion of this. Now, switching tracks entirely, when we switch over to the safety bit and we add that S here, we basically are taking things and we're saying, okay, so we've got an understanding of what our reliability is for this system. And we also have an idea of the criticality of the worst potential failure modes of the system. And so we're going to take a look at those worst case scenarios. We're also going to look at this from a regulatory perspective, because some of safety factors into regulatory, and we're going to take a small cross section of those things. And we're going to start to look at not just the safety of the individuals, but the safety of the environment we're working within. Safety has two definitions here. Where, generally speaking, we are focused purely on this, but since we don't have enough time to cover the regulatory and safety bits, I'm going to smash them together a little bit. So there's and Chris, you can attest to this, having worked directly in the field. You end up with the primary safety team, and then you've got an environmental team that's coming in after the fact and looking at everything and going, hey, so you covered all these things, but what about this spill that isn't a safety issue?
Yes.
And so for the sake of simplifying this conversation, let's just agree that regulatory and safety are going to be handled as one, and we're not going to talk much about the regulatory pieces, but I want to at least raise the level of awareness that regulatory is going to be a factor in all of this, especially once we add the S there. There's almost an implied E, which is the environmental factor.
Yes, good point.
But so when we're breaking out this from a pure safety perspective, we're taking those failure modes, and most importantly, those effects of the failure modes that are deemed most critical, and then we're reviewing the entirety of all of our systems, and we're combining the worst case scenarios plus the ones that are just a step down, where there's still risk, hazard, or danger involved. And then we're also combining the potential likelihood of those particular failure modes and their sort of subsequent effects or accompanying it. So as we're looking at bringing all of those pieces together, we're looking at the sort of combined criticality matrix of these things, and we're starting to get an idea of where the most actual risk comes in. And so this is where things like hazard analysis or HazOps start to come into play. And they are directly related to FMEA, but anyone who's done them will tell you that even though they look the same, and a lot of the outputs are the same, the way that you go through them is entirely different, because you're no longer as concerned with all of these other things which don't play into safety or don't play into hazards or risks. And suddenly you're saying, all right, what is the actual risk of this particular fault, or more importantly, in many cases, these series of faults that lead to a hazardous scenario, and then how do we start to understand and then go back and try to mitigate. Sometimes it's simple. Sometimes we just require warning labels. Sometimes we have to go back and we have to redesign a station or a operating scenario. And other times we discover that we've got something much worse. But the idea here is,
and in the case where there is something identified that's much worse, a lot of the time it's that introducing redundancy or introducing a safety override. It's not the end of the day. It's not the oh my god, we can't do this. It's flatten the project and forget it. We'll do something different. It's more a case of bringing in redundancy and safety overrides. Certainly in those cases. Yep. So I mean, taking what you're saying, you've got the failure modes coming in. So we've had this conversation before. I'll try and put a link in the chat at the bottom to last year's Tech Day. Myself and Sam, we talked about fault tree analysis and a bottom-up, top-down approach. What Sam's talking about now is a bottom-up, so bringing in those failure mechanisms and those failure modes and understanding what they are and putting them in at the bottom of the fault tree, and then they come together to produce a tree of events that leads up to a critical hazardous scenario. And in reverse, we've got the bottom down, which is as we said when we've chatted before, it's two hats, a reliability hat or a RAM hat and a safety hat. So you're switching between the two hats, and you're thinking of it from a different perspective. And where HAZOP comes in with the safety hat on, and it may be the same person that's doing the safety and the reliability. It certainly has been my case in the past of doing both jobs. And so we have that hazardous scenario. So I think we're moving on now into the fault tree mentality. So you have this hazardous scenario. You have created a fault tree analysis. You have your hazard, your undesirable event, what you don't want to happen, and you understand how that event could happen. And you create the fault tree. You go down this, and this could happen, and those coulds you then bring in the failure modes and failure mechanisms from the system or the subsystem and match them up. Where are the connections between these? How is it going to happen? And certainly, as you mentioned, environmental comes into it quite heavily, in that sometimes it's the environment itself that's causing the failure mode. Not necessarily you impacting the environment, it's the environment itself that's causing the failure mode. So something that's designed to work in ambient temperatures and just normal British temperatures maybe, and then suddenly you're expecting to work in the middle of a desert. You're going to create an environment that it's not necessarily been designed for, and you're going to generate new failure mechanisms. It is quite a lengthy process sometimes, trying to link up the undesirable hazard and identify what those things are that feed into it. And this is where the tools come in, where the tools help. Taking that. So Sam, do you want to expand on that with reliability block diagrams? How do they fit into this conversation?
Sure. So the big difference between reliability block diagrams and fault tree analysis is that they're sort of in more of a real way than where you've got the top-down approach of FMEA and the bottom-up approach of fault tree analysis, where you're sort of going from two different directions. Fault tree analysis and reliability block diagrams are sort of inverse functions, in that fault trees are really looking at how are all of the different potential faults that could stop our system, factored into the system, whereas the reliability block diagram approach is looking at what is my path to success. And so, I mean, they're the same thing. It's just we're choosing to look at it no longer from the perspective of, okay, so how is this going to fail? It's okay, so let's structure this instead from what are the paths to success? What are the paths to an operating system through this? And so we're defining all of the paths, and instead of just this bottom up approach where we've got all of our faults, we're instead taking it through a path through, and it's multi-pronged, and I don't have enough fingers to really show most most even somewhat complex systems in terms of the number of paths. But instead what we're looking at, okay, so what are all the constituent actual subsystems and subsystems and primary piece parts, and whether that's LRU, it's lowest replaceable or lowest repairable unit, or lower or higher, depending on your level of analysis. You're looking at it instead of from the fault perspective, you're looking at it from the system perspective. So you're talking about the actual constituent pieces. Generally, this is taking your bill of materials and representing that BOM in terms of kind of an exploded fashion. And I shouldn't use the terms BOM and exploded in the same sentence for obvious reasons, but it's accurate in this case. The idea here is that we're taking that and we're taking the expanded view of all of those things that are there, and we're sort of diagramming them from a path to success rather than a path to failure perspective. And they are the same in terms of the tool we have, BlockSim. We can do this from an analytical perspective, where we're just trying to get an instantaneous reliability point in time perspective, given the reliability policies we have, or we can use the Monte Carlo simulation, where we're taking all of the maintenance factors that we have and then running a number of simulations to get an idea of, instead of reliability, what the availability and maintainability of the system, and breaking down much more granularly all of the constituent piece parts that go into the system. Yeah. And so, the factor there is basically
nicely summarized. That is nicely summarized, Sam.
We need to be able to actually define the A and the M in RAM, and that's where BlockSim really specializes, and it's where RBDs specialize as a tool in terms of understanding what the availability and maintainability of your complex system is going to look like, either from a here's where we are now and where we'd like to get to today, or here's our proposal and here's where we think we're going to be on day one, and so we can start from there.
So once we've gone through the RAMS analysis and we've gone and done that, we've then got a handoff to the safety team for review. So you want to add a piece on that, Sam?
Sure. So, effectively, there's really two handoff places where things happen, and there's going to be some handbacks as well as the safety team discovers things and needs to update the RAM team on things. But so the first of these comes basically right after, or sometimes prior to, the conclusion of the FMEA / fault tree analysis, where we've first got our initial identification of what the critical factors are from a hazard perspective. In other words, not just, oh no, the system failed, now what? But it's, oh no, this particular thing failed in such a way that we have introduced a hazard. And so we hand all of those off to the safety team, and we go, okay, here's all the things we're doing from a reliability perspective. We're going to continue on this reliability path, but we're going to take the subset of these things, we're going to hand them to you guys from a safety perspective. Sometimes, as is the case with you, and as partially was the case with me, instead of handing it off, you go, okay, I'm going to take this, I'm going to sit it right here for a second, I'm going to switch hats, and I'm going to pick up this stack, and I'm going to ignore the reliability stuff for a minute, regardless of the fact that I really want to fix that too, and I'm going to focus on the things that if we don't get right, bad things happen. And so then we're going to focus on the safety aspects of these things, and we're going to stop worrying as much about the cost and about the downtime, and now we're going to think about things from still realistically still thinking about cost, but we're putting cost in terms of health instead of cost in terms of operations. And to be a little crass about it, there are associated costs with health, and so we need to be able to identify those and factor those into our total operating environment. And so we've got these safety factors, and we're going to go through them. We're going to understand, okay, is this risk properly handed off? Yes. Is this risk a real one that we believe could happen? Yes. And then we look at them and we go, okay, that's bad. Those two things are true. How likely is this to happen? And what could we possibly do to prevent it from happening? And if it's going to happen regardless, how can we reduce the overall severity of it occurring? And that's where all of the safety systems you were talking about earlier really start to factor in. So do we have a safe stop? Do we have cutoffs? Do we have lockouts? Do we have all of these things that when done in concert with the rest of our system provide for a much safer environment for us to operate in? And so then all of those things happen. And then we get to the end of all of this from the reliability perspective. So in an ideal scenario, this other team that's over here doing something, the reliability team has finished all these things. They've run it through an RBD. They've simulated it. They understand what the availability and maintainability of this thing look like. They come back, they regroup with the safety team, and they start talking about, okay, so here's what our overall reliability, availability, and maintainability statistics look like. They come back from the safety perspective and go, okay, well, here's the top 3, 5, 600 safety factors that we're dealing with, and
depending on the system that we were looking at,
and we start to integrate those two and get a better understanding of how likely these things are to actually occur. And this is where some of that reconciliation starts to actually play in. And so this is where some of the suppositions and ideations that the safety team had with regard to how frequently something is likely to occur either get validated or contested with regard to what their estimated frequency looks like. There's often some negotiation. Best practice in safety scenarios is to always assume worst case scenario, because you don't. And let's not talk about that. There's really good books on that subject. But the idea here is that you've identified what those things are, and you're starting to reconcile the entire process, and you start to bring in those safety factors. Part of the things that go on this with when you've got the safety hat on, or when you've got the safety team doing their thing, is you are going through HAZOPs. You're going through hazard analysis. You're looking at things from the perspective of, okay, so here's the sequence of things to a critical failure and critical series of effects. How do we mitigate that and cut it off upstream? And can we implement that into our system? What's the design rework of that going to be to impact things? Is there a design rework necessary? In other words, some things are just redundancy, which can be as minimal as having multiple signs. Some things require the entire duplication of an entire system. Now, we're talking about signs. There's no impact to any of the RAM pieces. But if we're talking about, okay, suddenly we have 2 of these things operating in parallel, or potentially operating in a standby scenario, suddenly a lot of the assumptions you had from both the reliability and from the availability perspective, and also maintainability, because you're suddenly maintaining 2 of these things instead of 1. Suddenly you have to go back and rerun some of the reliability pieces and get a better understanding of how the system's going to work with the reconstituted, but knock on wood, much safer system that you've got. And so, it's really about these handoffs, and then making sure, and this is the important part, that the hand back of all of these things that have been done by the safety team gets integrated in to the RAM piece of this. And that's where that S really, makes its impact and brings the value into the approach that you need to have, is those handbacks and the sort of integration and reconciliation of all that information results in a safer system that occasionally needs to be rerun.
Just capping off, we've got the reliability aspects, which we can analyze and bring in either with a block diagram or we can bring it in through the failure modes and effects analysis, and we can understand the reliability. And then using the FMRA, we can calculate that reliability. We can use a wireable analysis tool to do the maths if we've got some data. If we've got some figures from somewhere else, you can bring those in and create those for the reliability. We then run the simulation. A simulation gives us availability, so we can understand the availability. We can run that simulation in the RCM tool, but from a point in time perspective, so we get an availability as a fixed point rather than a simulated period over time. And then the maintainability using the RCM tool, understanding the maintenance tasks that are required, and understanding and analysing what we need to do to make sure that the system continues to operate safely or continues to operate reliably, but also with safety in mind. And we bring those together for the RAM. And with the maintainability from the RCM, we can put that also into BlockSim to create an reliability block diagram. And with that block diagram, we can bring in the maintainability aspects with that information, and then in there we can then also look at availability of crew, availability of spares, spare part pools, and so forth, a whole long list. And as a result of that, we've got then our favorite plot, the block up down plot. And the benefits of the block up down plot is where you can see when your system is down, and you can look to see how the system is down. So different aspects within your system are down for a particular reason. You can then see why they're down. Is it crew not available? Is it the fact that the system is further? So yeah, bringing that together, and we end up then being able to produce a fault tree analysis from all of that analysis that we pulled together. So this is where the RAMs part, the S, comes in on the RAMs, and we got that fault tree analysis. We've got a bottom up, and then we put our safety hat on, we're looking from the top down, and then we're feeding back through that process. So finally, we've got one last section to cover, so safety sign off before we conclude this video. And so we just want to cover that and a little chat about safety sign off, as really that's the end of the analysis and the end of the safety role to a point.
Right.
To a point.
Yeah, so I mean, it's really important, especially in cases where you're not working with a team, especially in cases where you are one and the same, the safety and reliability specialist, where you are taking your findings from the safety perspective and you're reviewing them with management and getting their buy-in and getting their agreement. And this serves its purpose for really two main reasons. One is it's a little bit of CYA in terms of, this is making sure that you've gone over this. But the other piece is that it's a bit of a sounding board. It's a bit of a perspective shift. It gives somebody else the chance to give you feedback on what your findings are and say, hey, that's great, I agree. Or did you think about this? And sometimes that's a drawing board moment. Other times it's a, yes, I did, and it's addressed here. But it's really important to have that conversation with management, especially in scenarios where you're doing both jobs, wearing both hats, so that there's additional perspectives that are brought in, and so that the underlying liability is shared with the rest of the corporation that you're working within, because as important as availability and reliability are from a liability perspective, the liability that comes with safety is tenfold, 100-fold more sometimes, and so it's vital that these things are reviewed with that level of import. And I just want to make sure that we, especially for those of you in the audience who are in that role where you are both safety and reliability, please review with someone else before it's just stamped and signed off and put into the world. It's important to have that conversation.
So thank you, Sam. That's been absolutely fantastic. We've covered a lot of different aspects there, and we brought those together for the reliability, availability, maintainability, and the safety story, and how things all integrate with each other. If you want to know more about the other topics, then, as we said before, go to our previous videos, because they talk about those topics in a lot more detail on where those come from, where it all comes from, to provide each step in the process as you go through that. So this video is focused purely on the feed of it into the safety and the bottom up, top down approach of the fault tree analysis, and who's talking to who. And as Sam pointed out, is changing the hat. Who's talking to who is most likely going to be yourself anyway, if you're in a safety and reliability role. But certainly, as we've said before in other topics, it is a team effort. These things are not individuals. These are teams talking to teams. And some people do have the overlap role between these teams, and it's certainly the best approach is to have that team feel. That's all from us. Thanks for watching. We'll see you at the next ReliaCast. The last one for Series 1 is ReliaCast 8. So I am going to be bringing that out before the end of the year to conclude Series 1. And it's been really good. Really enjoyed it. We've done a lot of videos, and thank you, Sam, for returning for video 7. And it's been an absolute pleasure having you here. And if there are any topics that you think we should be covering that we haven't, please put them in the comments down below. So somewhere down there, even if you're in LinkedIn or watching on YouTube, down there in the comments is where you can put what you think we should be covering. We do have a lot of feedback from other sources, hence the material that we've been covering during these videos, but we do want to hear more from you guys. If you do like the video, give us a thumbs up, like it, subscribe, the usual lingo for these things on LinkedIn and YouTube. So thank you for watching, and thank you, Sam.
My pleasure.
Goodbye.
It was